Here we're continuing with exercise 5-9, and here we just want to find all of the chiral centers and then see whether that each of those chiral centers is the right or left-hand version of itself, so R or S. And usually something that gives away that you might have a chiral center are these three-dimensional bonds, the bonds that are either going away from you, like the dashed wedge, or coming out at you, like the solid wedge. So those are places where you probably have chiral centers. Now you don't know, you should always check. So let's see, let's go through these one at a time, work through them one at a time. That starred carbon has a methyl group to the left, a bromine going down, a weird gigantic ring to the left, and the fourth thing is an invisible implied hydrogen. Now this carbon is tetrahedral, so you'll have two bonds in the plane, one bond going away from you, and the fourth bond has to be going out at you. So that hydrogen must be coming out at us. And that is our fourth thing. So you can see that that carbon with a red star on it is bonded to four different things, and so it's chiral. It comes in a right and a left-handed version, and those versions are going to behave differently. They're going to fit differently into the world around it and make other stuff behave differently too. So we need to figure out whether we have the right or left-hand version here. Now to do that, we're going to follow those CIP rules, those Kahn-Ingold-Prelog rules. Excuse me, and the first step is to assign priorities based on atomic number. Now for hydrogen, the atomic number is the smallest on the periodic table, which is 1. So hydrogen has 1, carbon is 6, the other carbon 6, and bromine is 35. So the highest atomic number gets the highest priority. Here that's bromine, that gets the number 1. The lowest atomic number gets the lowest priority. Here that's hydrogen, that gets the number 4. So now we're down to the carbons. If atoms ever tie, then you make a table. So I'm going to make a table for the carbon on the right and a table for the carbon on the left. And ask yourself, what three things is that bonded to going away from the chiral center? So this is bonded to a carbon, and an oxygen. We put those in order of descending atomic number, so the oxygen has the highest, and then the two carbons. For the carbon on the left, that's bonded to 3 implied hydrogens. So we'll write those down. And once you have the tables, you compare them. You don't look at the whole thing at a time, just one row at a time, and only if that top row ties would you go down to the second row. But here it doesn't tie. The oxygen has the higher atomic number, and so the carbon bonded to that oxygen has the higher priority. So now we have our priorities. That's the first step, assigning priorities based on atomic number. The second step is making sure that 4 is going away. 4 is not going away, it's coming out at us. Now what that means is we're still going to go from 1 to 2 to 3 and see whether we're going clockwise or counterclockwise. But whatever configuration we would think we would get from that, we have to switch because 4 is coming out at us. So if you go from 1 to 2 to 3, you are going counterclockwise. And because of that, you would think that this would be the S configuration, the left-handed version. But because 4 is coming out at us, you switch that, and it's actually the R configuration. This is the right-handed version of this chiral center. So that's our first chiral center. Looks like we might have another one right next door. Let's just check to see. On the left, we have this big group with the bromine. Interesting. On the right, we have a ring with like an oxygen and a straight chain. Going up, we have a ring with just carbons. And going down, we have a methyl group. So those are 4 different things. And so that atom with the red star on it is a chiral atom. And it comes in a right and left-hand version that will behave differently, and we want to know which version we have. So the first step is to assign priorities based on atomic number. Oxygen has an atomic number of 8, carbon has an atomic number of 6, carbon has an atomic number of 6, carbon has an atomic number of 6. Well, we know that the oxygen with the highest atomic number will get the highest priority, so that'll be a priority 1. For the other 3, we have to make tables because they all tie. So I'm going to make a table for this carbon at the bottom, a table for the carbon on the left, and a table for the carbon going up. At the bottom, going away from the chiral center, this carbon is bonded to 3 hydrogens. To the left, going away from the chiral center, this carbon is bonded to a bromine, a carbon, and a hydrogen. So bromine has the highest atomic number of those, then carbon, then hydrogen. And actually, let me just move that up a little bit. And then the carbon at the top, going away from the chiral center, is bonded to a carbon and 2 implied hydrogens. So now we can compare these. We're only looking at the top row, and only if the top row ties would we go down to the next row. Of these 3 tables, the carbon on the left is bonded to an atom with the highest atomic number. So that'll get the next highest priority, which is 2. Between the 2 that are left, the one at the top is bonded to an atom with the highest atomic number. It's bonded to a carbon, which is higher than the hydrogen there. So that gets the next highest priority, 3, which means that the methyl group at the bottom will be our 4 here. So that's the first step, assigning priorities based on atomic number. The second step is making sure that 4 is going away. And here, thankfully, it is. That's the easiest case scenario. So if 4 is going away, go from 1 to 2 to 3. Here we're going clockwise, so this is an R configuration. Because as you go from the top of an R, you can remember that because as you go from the top of an R to the bottom, you go clockwise. And so the handedness for this chiral center is R. So far we found the chirality, the right or left-handedness for 2 of our chiral centers. Looks like we might have another one really close by, this one right here. So let's see, let's make sure that that really is chiral. It's got this weird branch to the left with a double bond in the chlorine. It has an oxygen, the chlorine branch was to the right. It has an oxygen to the left. It has a carbon branch going above, and that's different from any of the other highlighted groups. And then the 4th thing it's bonded to is implied. It's not drawn in, which means it has to be a hydrogen. Now, a tetrahedral atom has 2 bonds in the plane, 1 going away, so the other atom must be coming out at you, so that's going to be our hydrogen. And that is a 4th different thing here. So that start atom is a chiral center. It's bonded to 4 different things. So it's going to come in 2 versions, a right-handed version and a left-handed version. To figure out which one we have, we use the CIP rules, the Kahn-Ingold-Prelog rules. So the first step in that is to assign priorities based on atomic number. Oxygen has an atomic number of 8, carbon 6, hydrogen 1, carbon 6. So the highest atomic number for oxygen gets the highest priority, 1. The lowest atomic number for hydrogen gets the lowest priority, 4. The 2 carbons tie, and whenever atoms tie, you make a table. This carbon on the sort of bottom, on the right, going away from the chiral center, that's bonded to a carbon and 2 implied hydrogens. So in descending atomic number, carbon, 2 implied hydrogens. The carbon at the top, going away from the chiral center, is bonded to 2 carbons and 1 implied hydrogen. So now we are going to compare these tables 1 row at a time. The top row ties, so then we look at the second row. And the second row doesn't tie. The carbon on top is bonded to the atom with a higher atomic number, and so the carbon on the top gets the higher priority. So now that's the first step, assigning priorities based on atomic number. The second step is to make sure 4 is going away. 4 is not going away, it's coming out at us. And so what that means is we're still going to go from 1 to 2 to 3, but we're going to have to flip the configuration that we would otherwise expect. So if we go from 1 to 2 to 3, we're going clockwise. So you would think that it would be R, but 4 is coming out at us, so we flip it, and it's actually S. And the only reason we're flipping it is because 4 is coming out at us. So this chiral center here is the left-handed version of itself. Okay, well, we've assigned chirality to 3 chiral centers. We just have one more here, this one at the top. Let's check to see if that really is a chiral center. So we've got a weird branch that hits an oxygen 2 away, and that is another branch coming off of it with a chlorine. That's one thing. We have a ring with just carbons on it for a while. That's definitely a different thing. We have a methyl group. That's a third thing. And the fourth thing is an implied hydrogen. You'll notice this carbon doesn't have a formal charge, so it does have 4 bonds, but only 3 are drawn. The only atom that can be there without being drawn is a hydrogen. And because two bonds were already in the plane and one was going away, this fourth bond to the hydrogen had to be coming out because it's a tetrahedral molecule. And that hydrogen is different from any of the other 3 things. So that carbon with the red star on it is indeed chiral. It's bonded to 4 different things, and the significance of that is that it comes in 2 versions, a left-handed version and a right-handed version, that both fit into the world differently. So we need to figure out which one we have, and we'll do that by assigning priorities based on the atomic number. The carbon to the left has an atomic number of 6, the carbon to the right has an atomic number of 6, the carbon at the bottom has an atomic number of 6. So those all tie. But the hydrogen has an atomic number of 1. That's the lowest atomic number, so that gets the lowest priority, so that's going to be 4. For the carbons, whenever atoms tie, make a table. So we'll make a table for the carbon on the right, a table for the carbon on the left, and a table for the carbon at the bottom. The carbon at the right, going away from the chiral center, is bonded to 3 implied hydrogens. The carbon at the top, going away from the chiral center, is bonded to a carbon and 2 implied hydrogens. And the carbon at the bottom, going away from the chiral center, is bonded to an oxygen, a carbon, and an implied hydrogen. So we compare these tables one row at a time. First, just looking at the top rows, we see that none of them tie. The one at the bottom has the highest, is bonded to an atom with the highest atomic number, so that ends up getting the highest priority of 1. Of the 2 that are left, the one on the left has the highest, is bonded to an atom with the highest priority, the carbon, as opposed to the hydrogen. And so that gets the next highest priority, a priority of 2. And the methyl group here gets the priority of 3. Hydrogen is 4. So that's the first step, assigning priorities based on atomic number. The second step is making sure that 4 is going away. Here, 4 is not going away, it is coming out at us. And what that means is we're still going to go from 1 to 2 to 3, but whatever we would predict doing that, we have to switch that configuration to its opposite. So for example, if we go from 1 to 2 to 3, we're going clockwise. So you would think this would be R, but because 4 is coming out at us, we have to switch that thought. It's actually S. So this chiral center in red with the red star on it, that is actually the left-handed version of itself. The configuration there is S. So that is assigning the chirality, assigning the chiral centers for all the molecules in this cumipalaxane, which is a signal agent produced by a snail indigenous to Guam. All right. For this next molecule, our last example of going through these chiral centers and assigning configuration, you'd first want to look for the chiral centers, and one of them you have right at the top here. Well, one of them should seem suspicious, the one at the top, because it has that three-dimensional bond that is coming out at you. And usually that three-dimensionality is only really significant if you're trying to tell the difference between right and left-handedness. So let's check to see if that truly is chiral. Well, we have this benzene ring with what's called a nitro group on one end, the NO2, on one side, so that's one thing. We have a OH, that's called an alcohol, going up. We have a weird, large group to the right. And then there's another fourth thing. Now, only 3 bonds are drawn, but that carbon doesn't have a formal charge, so it must have a fourth bond. The only atom that could be there without being drawn in is a hydrogen. And because there was already 2 bonds in the plane and one coming out at you, the fourth one had to be going away. Tetrahedral atoms will always have 2 bonds in the plane, one coming out at you, and one going away. So here, this is chiral because that hydrogen is a fourth thing, so that carbon with the red star there is bonded to 4 different things. And so it's going to come in 2 versions, just like your hand does, a left-handed version and a right-handed version. Those things fit differently into the world. And so we need to figure out which version we have here. So the first step is in using those. So to do that, we're going to use the CIP rules, the Kahn-Ingold Prelog rules. And the first step in those is to assign priorities based on the atomic number. Now, the atomic number for the carbon on the left is 6, for the oxygen is 8, for the hydrogen is 1, for the carbon on the right is 6. Oxygen has the highest atomic number, so that's going to get the highest priority of 1. Hydrogen has the lowest atomic number, that's going to get the lowest priority of 4. The carbon on the left and right tie. So whenever atoms tie, make a table. I'm going to make a table for the carbon on the left and for the carbon on the right. Going away from the chiral center, this carbon is bonded to 1, 2, 3 carbons. It's bonded to carbons 3 times. For the other carbon, going away from the chiral center, is bonded to a nitrogen, a carbon, and an implied hydrogen. We put those in descending atomic number in our little table. Now that we have the 2 tables, we compare them, one row at a time. We can see the top row doesn't tie, so we don't even have to think about the second or third row. The carbon on the left is bonded to an atom with a higher atomic number, so that gets a higher priority between the 2. So that's the first step, assigning priorities based on atomic number. The second step is to make sure that 4 is going away, and here it is. That makes our life very easy. We just need to go from 1 to 2 to 3, ignoring 4. Going from 1 to 2 to 3. Here, that means we're going clockwise, and so that means that chiral center is the right-handed version of itself. It is R. Now we don't have to switch anything because number 4 was going away. So that chiral center is the right-handed version of itself. There's one other atom here that looks like it could be chiral, and that's this atom right next door. It has that 3-dimensional bond, the solid wedge coming out at us, and so let's check to see if that is chiral. To the right, we have a sort of alcohol group, the OH. To the left, we have a weird alcohol with a benzene ring, and then that nitro group. Going down, we have a nitrogen with a carbon double bond to an oxygen next door. That's something called an amide. So that's a new thing. And then, if you notice, this carbon does not have a formal charge. So it must have 4 bonds. Only 3 are shown. The only bond that could be there without being shown would be a bond to a hydrogen. Now, because this carbon already has 2 bonds in the plane and 1 coming out at us, that 4th bond to the hydrogen had to be going away. Well, that's a 4th thing. So the carbon with the red star there is indeed chiral. It has 4 sides. It's bonded to 4 different things. So we want to know, so that means it's going to come in 2 versions, a left-handed and a right-handed version. And we want to know which version we have here, because the 2 versions fit into the world differently and have a different effect on the world around them, including on the living things around it. So to figure out which version we have, we're going to use the CIP rules, the Kahn-Ingold Prelog rules. And the first step with those is to assign priority based on atomic number. So the atomic number for the carbon on the left is 6, for the carbon on the right is 6, for the hydrogen is 1, for the nitrogen is 7. The highest atomic number, 7 for nitrogen, gets the highest priority, so 1. The lowest atomic number, 1 for hydrogen, gets the lowest priority, so 4. The two carbons tie, and anytime two atoms tie, you want to make a table. The carbon on the left will have a table, and the carbon on the right will have a table. Going away from the chiral center, the carbon on the left is bonded to an oxygen, a carbon, and an implied hydrogen. On the right, going away from the chiral center, it's bonded to an oxygen and 2 hydrogens. Now that we have the tables, we can compare them one row at a time. The top row ties, so we look at the second row. Here, the carbon on the left is bonded to a higher atomic number atom, the carbon. And so, the carbon on the left gets the higher priority of these two. It will be 2, the other one will be 3. So that's the first step in the Kahn-Ingold-Prelog rules, assigning priority based on atomic number. The second step is to make sure that 4 is going away, and here it is. Huzzah! That is the easiest case. Now all we have to do is to go from 1 to 2 to 3. And because we're going clockwise, this is going to be the right-handed version of this molecule. You can remember that because going from the top to the bottom of an R, you have to go clockwise. So this chiral center with the red dot, that is the right-handed version of itself. And even if this whole molecule were exactly the same, all the atoms were there, they were all connected the same way, but this chiral center were the left-handed version of itself, it would not function as an antibiotic. That's the significance of that handedness. So in this molecule, we saw there were 2 chiral centers, and we saw how to assign the configuration for those based on the Kahn-Ingold